Hello, my name is Wenming Yi. I am a technical evangelist on the Windows Azure Evangelism team. Today, I will cover the topic of a simple introduction to big data and Hadoop. So in this presentation, we'll go into some more of the details of big data problems that we're experiencing, how new technologies such as MapReduce are used to cope with it. So you'll find some of the basic fundamentals of big data, and then I will demonstrate what we have done with Hadoop at Microsoft. Hadoop is an open source MapReduce solution, and the symbol for Hadoop is the little happy elephant that you saw on the front page. In one sentence, the answer to the question is that we're generating more data than we can possibly analyze. So what is the concept of 1.8 zettabytes of data that we generated in 2001? So a zettabyte is roughly 1.8 times 10 to the 21st power. So that's a really large number. And there are 1.3 billion people in China. So we'll have to have every single one person in China fill up a 1.5 terabytes of hard drive with content in order to get that 1.8 zettabytes of information. So if we were to do that with the US population, everybody will have to work 4 times as hard. So you have to fill out 4 drives with content in order to generate that 1.8 zettabytes of data. So if that didn't look bad enough in 2011, in 3 years, or by 2015, the world will have to ask the entire population, which is 7.2 billion people, and each one of them will have to fill out a hard drive of a 1 terabyte hard drive with content. And we haven't even discussed another 3 years down the road here. So let's look at how the data is being generated. So here are some of the examples. Bing ingests about 7 petabytes of information per month. And the Twitter community, which we're all familiar with, even though the tweets are 140 characters or less, but we generate about 155 million tweets per day. So for the US population, it's almost every other person is writing a tweet every day. And we're not counting the growth potential of more people in the world are going to tweet every day. So the source of data are from devices, internet, websites, weblogs, government data, and sensor instruments. So a lot of these data are being generated in a fashion that is automated, and what we are seeing such growth in the amount of data that's being generated is that if we just look around us, that every device that we carry, and we're carrying even more devices every day. So these devices are being getting more powerful. That includes your computers and now cell phones, which are much more ubiquitous, and you can carry them around. They're portable. And these devices, when they become more powerful, they consume more data. So at the same time, these devices are actually getting cheaper. Our computers are getting cheaper. And the simplest example is your digital camera and cell phones. They are pretty much everywhere these days. Just about every person in the US or many other countries have one of these devices. So another reason why we're storing more data is because storage is actually getting cheaper too. So finally, these devices are also getting easier to use. Computers are getting easier to use. Your phones are getting easier to use. Cameras and other portable electronics. So they are suddenly also being made more accessible to a population, a larger part of the population that didn't have access to them before. So in fact, the global information is growing faster than the availability of the cheaper storage. To illustrate this problem, The Economist recently published a special report on the data deluge. In this report, they're basically indicating the same problem that we alluded to earlier, which is that data is growing much faster than the rate the rate that we're able to store them and analyze them. The equipment that we have today is capable of generating more data than we have ever been able to generate in the entire human history in 5 years. So essentially, the next 5 years will also generate a lot more data than we have ever done in the previous human history. So the data is doubling or tripling every 5 years or so. So here's an example scenario in the enterprise. So in the traditional e-commerce data flow, here's an example of a online store that new user registrations and new purchases and additional products that you have to add to a catalog are stored in a traditional relational database management system. And the data is usually very well understood and they're very well defined. In a new e-commerce big data flow, in addition to the data we have to worry about in the relational database, we will also need to analyze the unstructured data that we previously discard or not able to analyze. These unstructured data sets that we can extract very useful business intelligence information from, and then we can take that useful information and store it in the enterprise database. In the previous example, the log data are often so large that they can't be moved easily on the network. Like any big problems that we're trying to solve, the best strategy is always divide and conquer. So I have been doing a lot of HPC programming for the last few years, and that is also the same strategy that we use to conquer large HPC or computational intensive problems. So instead of being able to distribute your compute or CPU intensive workload across a cluster, here you're taking the I/O or the data stored across a cluster in order to store a huge amount of data. So the data has to be stored on multiple computers. So the second problem is that the data are too big. So these data cannot be moved across the network. So the solution is that we have to have a system that can help move compute code closer to the machine where the data is located on the cluster. There are 4 V's associated with the big data, namely volume, variety, variability, and velocity. So volume of data it means the amount of data that we have to deal with. Variety of the data means that we have data from different sources, especially for new data sources. They're also in very different formats from the different data sources. Variability, a lot of times that data are interpreted differently by different sources. And finally, velocity is the rate of which the data is being generated and moved. So these characteristics means that the data analysis becomes much more complex, but it is also generating opportunities for tools. But it is also allowing us to ask new questions because of the availability of these tools and gain new insights into these big data sets that we previously are not able to analyze. The first thing you want to do for a MapReduce operation to actually take your data set and copy it onto a distributed file system. So In the case of Hadoop, we will later show you how the architecture of Hadoop looks like. So essentially, taking your data and copying onto a distributed file system called HDFS. So the second step, so we have to process the data. So there are two steps involved in MapReduce, and the first part is the map. So the way it works is that you actually take your code and map it to the computer that is on your cluster where the data needs to be processed by that particular piece of code. And the second operation is the reduce operation. The reduce operation simply summarizes the results from each of the map process, which are parallel, and that is the simplest explanation of a MapReduce operation. So a MapReduce job splits the input in a data set into independent chunk of work so that they can be done in parallel. These 4 steps are a very important part of the MapReduce workflow. Data acquisition and modeling, being able to get the data. Collaboration and visualization. Being able to look at the data is probably the easiest way to be able to analyze and figure out what the correlations are for your data set. And analysis and data mining, this is where the actual MapReduce operation comes in. And you're using the machines to analyze and data mine the actual data set. Dissemination, sharing, and preservation of the data. That's also very important. Being able to share the data with multiple researchers is an important aspect of scientific collaboration. These methods mentioned here are not just unique to big data. In fact, they are already part of a very typical workflow for analyzed data sets. Hadoop. So let's look at the basic architecture of Hadoop. So in the previous section, we already looked at what MapReduce looks like. So MapReduce, the Hadoop is an implementation of MapReduce engine. So it consists of 2 parts. One of the first part is the lower layer, which is the distributed file system. So it consists of HDFS layer. What it's doing for you is to be able to distribute your data set automatically across a cluster. And the way HDFS typically works is that it keeps 3 copies of your data so that it also takes care of redundancy. So if you have any of the nodes do fail, it would be able to replicate that back and still keep the integrity of the data. And then there's the MapReduce engine. As we mmentioned previously, there's the MapReduce tasks. There are many stages to them as the mapper become the input, the output of mappers, which run in parallel, become input to a reduce job. So you need a system that keeps track of where the data is, so you can send that mapper to the code that you need to run to where the data is to operate on a specific set of data. Here is a comparison between a traditional relational database management system versus MapReduce. So the traditional database is fully capable of holding gigabytes or even terabytes of data. And you can do read and writes relatively fast, and the access is usually interactive, and I can type a SQL query, or I can run a batch query overnight if I wanted to. And you do a lot of read and writes to the database system. The schema is very restrictive and it's static. So once you made it, it's the table. If you alter your table, you essentially have a very different schema than what you had before, and you might break the code that talks to it. And another very important aspect of traditional RDMS is the ACID property. The scaling is nonlinear, and dBA ratio is 1 to 40. For MapReduce operation, you would be able to operate on petabytes of data, or in the future, perhaps hexabytes. It's very much a batch-oriented system, just very similar to it's very similar to HPC, where you are doing large compute that takes a long time, and here you're processing data, and that takes a long time. And the data is in general written once, and they're read multiple times, but not necessarily modified very much. And the schema is dynamic. You are able to hold a lot of different types of data, and the integrity is relatively low because there's generally a lot of bad data, and when the amount of data is huge and we don't necessarily have a schema to restrict it. The scaling is linear. It depends on how many nodes you have. And that's the key here, which is the ability to scale, since it's more or less an embarrassingly parallel problem. But in this case, it is for the ability to host or store data using multiple computer nodes. So here's a look at the Hadoop ecosystem. So let's look at the lowest level first. The HDFS, or the Hadoop Distributed File System, is sitting at the bottom, which is the basis for all the other software that runs on it. You have to be able to have a reliable distributed file system to store the data first before you will be able to do operations on it. The next level we're looking at is HBase. HBase is a column-based database. So it differs a little bit than the Hadoop MapReduce operation by the fact that you actually can operate a lot more read and writes to the database rather than just simply doing a lot of reads and never modifying the data very much. And on top of the MapReduce engine, you have Pig, which is uses the language called Pig Latin to give you a data workflow engine. In fact, you'll see that we here at Microsoft has a group that took JavaScript and be able to compile it down to Pig Latin to run our JavaScript MapReduce operation. And Hive is an interactive, very much SQL-like. In fact, it is almost a superset. It's a superset of SQL. So it allows you to interactively look at your data. So you can create a table, you can drop a table, you can do your select, and finally Scoop. Scoop is a way for you to massively import data in and out of our relational database management system. So here is a look at the details of our offering. So first, we are offering a modified version of Hive ODBC driver, and there is also a Hive add-in for Excel. So we'll be demonstrating that in a few minutes here. It's also integrated with Microsoft Power Pivot. The Hadoop offering we are making is also enterprise ready. Hadoop-based distribution for Windows Server and Azure will be released, and we also have a strategic partnership with Hortonworks, which is an expert in this area. And finally, we have created something new for the Hadoop ecosystem, which is the JavaScript framework. So it makes the MapReduce operation extremely easy to script, and anyone with the knowledge of JavaScript would be able to run these large-scale distributed MapReduce operations. Here is a more complete view of the big data offerings that we have. At the bottom layer, we support both structured and unstructured data sources. The next level up, for storing the data, we have Hadoop on Azure and Hadoop on Windows Server for unstructured data, and Microsoft Enterprise Data Warehouse for structured data sources. As for the Business Intelligence Platform, we have SQL Server Analytics Service and SQL Server Reporting Service, respectively. And finally, at the top, we have tools that are familiar to our users to be able to analyze and visualize the data interactively. That includes Power View, Excel with Power Pivot, and predictive analytics, and also embedded BI offerings. So here is a first look at being able to deploy and interact with a Hadoop cluster on Azure. So there will be 3 parts for the demo. The first part is to show you how easy it is to deploy a cluster. The second part is to be able to run a simple MapReduce job using JavaScript that we mentioned earlier. And finally, we have a demo that shows you how to use Hive to interact with the cluster and be able to visualize the results from Excel using the Hive ODBC driver. Hadoop on Azure is hosted on Hadoop on Azure.com. So if you look at the sign-in page by simply clicking on Sign In, and it will take you to a Welcome Back page, and you can simply type in a DNS name of your choice and choose a size of a cluster and type in your username and password to create a cluster. This is probably the simplest way for you to create a cluster on Windows Azure. So I'm going to type in MR02, which stands for MapReduce 02, and a small instance. I'm going to type in test user, and I'm going to type in my password. Looks like I need to there it goes. My password now matches. And I can simply click on Request a Cluster. And that is going to create a cluster for me on Windows Azure deployed there. And of course, you can deploy a Hadoop cluster on your Windows Server cluster, as well as doing the same in your own environment by creating a hosted service and deploy that using the tools that we'll make available to you. So this is going to take approximately 15 minutes or so, just like your normal Azure deployment process. So instead of waiting for this cluster to deploy, we'll actually show you a cluster that I have already deployed. Here's a cluster that I deployed earlier. As you can see, you have about 2 days to play with the cluster before it expires. You can always release the cluster earlier if you no longer need it. Here's a look at the control panels. So you have JavaScript and Hive as an interactive console, and you have the ability to remote desktop into the head node to control the cluster, and you can control the security of the cluster by turning on and off FTPS as well as ODBC driver. Finally, the Manage Data panel lets you import and export data from your local computer, as well as the blob storage on Azure, Amazon S3 storage, as well as the data markets. If you click on the data market, you simply have to enter your username passkey from the data market and a simple query. Then you can pull all the data into a Hive table of your choice. Let's take a look at the interactive JavaScript console. Here's a look at the interactive JavaScript engine. You can type any HDFS commands right there from the JavaScript. And if I just type !, you can see that allows me to do ls and cat. All these operations can work on the HDFS file systems. If I do a ls, it will show me that all the files that I already have up there. So if you want to upload a file from your desktop, you can simply type fs.put, and it will bring up a file dialog box right there, and we can pick perhaps another file to upload. So there you go, and it's just that easy. So the next step is actually we want to take a look at the word count program that we want to run. So I want to cat the file, and as you can see, it's a very simple MapReduce program, and it's simply taking a document and splitting it by non-alphabets, and that simply produces you with a list of words, and then you're trying to do a count and summarizing how many numbers of each of the words there are. And this is a very much a classic MapReduce program for search engines, where in general people are trying to take an article, making it into a vector, and try to compare it with a very large matrix of existing articles. So let's actually run the query. So I already have it copied, so I can simply paste the query. What we're trying to do is to run the MapReduce and order it by the number of the largest number of words, and I want the top 10, and put that into a file called GB top 10. So the job has been submitted, as you can see, and underneath the JavaScript engine, we actually compile the JavaScript into a Pig Latin format so that you can run it as a Pig Latin job. If I run that, as you can see, we have 1, 2, 3, 4, 5 stages for this particular MapReduce job. So as any big data jobs, it will take a while to finish. Just like an HPC job, we generally use a batch system, and we wait for the process to finish. And it could generally take up to 5 minutes to complete. In the meantime, we can actually take a look at the log to see what it's actually doing. So it's executing the process, and we are at about 20% completion, and it will probably take up to another 2 to 3 minutes to finish. So we will wait. It looks like our MapReduce job just finished. Let's take a look at what the output looks like. And we actually have some results. So let's read it into a file and try to plot it. Looks like D, off, and those are some of the top words that appears in that article. So let's actually try to plot that. But the first thing we have to do is to actually parse the data and put it into a vector. You can use the parse function to do that. There we go. And to do a plot, you can simply call the graph object. And here we go. So it looks like D is the number 1 by far that appears in that particular file. The next example I'd like to show you is to use the interactive Hive console. So Hive is just like SQL, and you can type commands like show tables, and it will show you all the tables that I have already preloaded onto the cluster. Looks like I have some crime data that I imported previously from the data market. So you can do a select star from crime data, and let's limit that to 10 and take a look at what the table roughly looks like. That's interesting. So let's run a more interesting query and try to figure out some of the top violent crime cities in the US. So here is a pre-written query that I have. The only difference is that my table is has a different name. So let's go ahead and run that query. So once again, this is a batch program that's being mapped onto a 8-node cluster. So we're going to have to wait for a little bit. It did take about 2 minutes, and the results did come back. And it looks like New York is by far the that holds the most number of violent crimes, just because it's a very large city. And that's followed by LA and Houston. So I actually ran another query which saved the results into a table so that we can pull it up using Microsoft Excel, and I saved it in a table called results. And there it is. So the next thing I'd like to do is to go to Excel, and here's the data panel, and you'll find the Hive panel that I installed earlier. So we want to enter our cluster details. Okay, connect. Looks like we can actually select the results table and simply execute the query by selecting both the city and the violent crime, and execute the query. The data came back, and we can select the data and plot them. Our Hadoop on Windows offering has 3 big differentiators. The first piece is insight and tools on visualizations. We offer Excel, Power Pivot, and Power View to be able to operate on Hadoop data. Second part is that we're enterprise ready. So there is integration through Active Directory, as well as being able to use System Center to manage the cluster. And finally, broadening the access to a lot more users. So you have the flexibility of choosing to deploy your cluster on Windows Server or on Windows Azure. So for Windows Azure deployment, you don't have to have any hardware deployed on your local cluster, and the startup cost is almost zero. And we also simplified the installation and configuration of Hadoop. And there are 2 new offerings that, in terms of programming language for Hadoop. One is that we integrated JavaScript engine so that you don't have to write any Java code, and it also replaces the Pig Latin workflow engine using the same JavaScript, so that you can have an integrated experience to be able to interact with the cluster. With the addition of Hadoop ecosystem, we're extending more offerings for data warehouse solutions, making it more flexible to all users from startups to enterprises. We're also announcing our partnership with Hortonworks, We will provide an end-to-end Hadoop-based solution to enterprise using both Windows Server and Windows Azure. And finally, Microsoft is committed to broaden accessibility of big data technologies to end users, developers, and IT pros by making them match commercial quality and usability. Here are some more resources. You can go to Hadoop on Azure directly to look at what type of offerings we are providing, as well as any news on Hadoop on Azure. And finally, the Hadoop.apache.org is always a good resource to learn more about MapReduce and big data technologies. Thank you.